Okay, everyone, welcome back. So now we are into the lecture number 21, that is the control of the processor. So this is actually the second part of the processor that we started from last lecture. So let's just go through with a little review of the last lecture before going to doing the main thing here. So what will we learn here? The basic processor design that we actually started from last lecture. Um, After that, the main topic for today's one is about the control unit for the basic design that we studied, and we'll see how different instructions, how the processor data path works for different instruction, different types of instruction that we are actually we are doing a subset of the whole MIPS instruction set. So those instructions, how they are actually executed inside the data path. So we'll be seeing how the flow of the instruction takes place. So next thing, the roadmap so far. This is the whole course. What we have done, what we are currently doing, and what's up ahead. So performance, abstraction, instruction set architecture, arithmetic, ALU design, multiplication, division, floating point, and then from the last lecture we have started the study of the processor, the MIPS processor, the basic implementation. The actually that implementation includes a subset of the whole instruction set, not all the instructions, but some of the basic and important instructions are implemented. We can add more instructions to it as a task, as an assignment for you, but the basic instructions, the subset instructions that are given, the instructions that are actually included in the implementation. And what's up ahead that we are going to do today is data path control. So let's just take a review of the last few slides that we did in the last lecture. So the second part of the data path, that was about register file, the registers, the ALU, and the data memory. So that is actually the second part, apart from the instruction fetch data path that we studied in the last lecture. So this is actually the whole data path. After instruction fetch, all the instructions actually pass through these modules and complete different instructions accordingly. So for an R type instruction, what happens? Register number 1 RS is read, register number 2 RT is read, RS is passed to ALU, RT is passed to ALU through this multiplexer. That ALU SRC is the multiplexer that actually controls which should be the second input to the ALU. So for a R type instruction, that ALU source will have a value of 0 instead of 1. So and after that, for an R type instruction, the ALU will do some operation. That operation is basically selected by this ALU operation bit. Now you have to have that understanding of ALU that we studied from the chapter 3 of ALU. When we studied the design of ALU, we had 4-bit select signal for the ALU that actually selects different operations of the ALU. The operation actually specific to the MIPS architecture, the MIPS instruction set architecture. So these ALU 4-bit operation field is actually the same thing. So you should have that understanding as well. So what happened in the second part of R type instruction? RS is read, passed to the ALU first input. The RT, the second register, is passed to ALU as a second input, and then whatever the operation that is set in that R type instruction, after executing in the ALU, the result is basically is the output of the ALU. That output, this is going to be saved back to the registers in the RD. So this is RD, where the register, where the destination, the result of ALU is actually stored back to register. So how is it stored? It actually passes through another multiplexer. That multiplexer is basically selecting the destination which data is to be stored back to register as in the final step. So this is how a R type instruction works. Similarly, what happens in a load instruction? So load instruction is actually similar to R type, but the thing is, for an load instruction, the data is actually read from the memory. So let me just write a few instructions here. So this is your so this is an R type instruction. So for an R type instruction, there is an RD as a destination. So whatever that is, we have got an RS. This is one of the source, and we have got an RT. So both RS and RT are the source registers for an R type instruction. So these RS is basically this one. This will be RS. That will always be RS, because even in load word instruction this will be RS. This is RT, that is read here, that is read from the register file. So this is so this is RT. So RS is read first and RT is here. So this is an R type instruction. The destination, whatever the operation is, AND operation is selected by this operation field. This will select what operation is going to do. Is an AND operation, and after that the result, whatever the result is between an AND operation of these two source registers, whatever those source registers are. So the result is basically passed to the register write data field through this multiplexer. So that data is actually written back. But where is it written? This RD is the destination, and this RD is basically passed to the write register number. So this RD is the register number. Register number is actually passed to the write register field of the register file. So this is how a R type instruction works. What happened in a load word instruction? So let's just write a load word instruction as well. So what happened in a load word? Load word is a little different. So let me just write actual registers here. So this is dollar S0, S2, comma 100 is the offset. We know what this means. Let's see, just 4 is the offset to keep things simple, and dollar S 4 is the RS here. So this is an RS load word instruction. This S4 is here. S4 is the RS. This S2 is the destination, which is not RD. Instead, it's RT. So this is your RT, which is used as destination. So what happens? One main difference in this data path will be like this destination in R type instruction, the destination register was RD, but in this instruction the destination register will be RT. So this write register is also, it also needs a multiplexer here somewhere. So there has to be some multiplexer. So multiplexer is missing here. So RT is a destination for a load word instruction. What's the source? It is actually the some memory location that is present in the memory. So what happens, this is actually where the address of memory comes from. So this is RS, your the S4 in this scenario is your RS. So what is RS? RS is the base address of the memory where the data is actually being fetched. 4 is the offset that comes from the this constant field, 16-bit constant. The 4 comes from there. It will be transferred. It will be sign extended to 32-bit and passed here. So what happened in the load word instruction? Register 1 is RS. Register number S4 register is read here. So S4 comes here. So that goes to the first input of ALU. So what happened to the second input of ALU? It's not an R type instruction, it's a load word instruction. So it means the second input to the ALU is actually coming from the constant. So this is that 4 number which is in this instruction. So that 4 is transferred to the second input of ALU through that multiplexer. So ALU source control signal will have some value. So this is passed to ALU. ALU, what ALU does here? ALU has a fixed operation for load word. And what's that operation? We know that it just calculates the address, the the address of the memory where the data is to be read from. So that data is passed to the memory. That address field will have that address, and there will be either memory read or memory write. So for a load one instruction, the operation is memory read. So memory read is here. Memory read means the read data will have the value of the location of the data that is placed in the location that corresponds to that specific address. So that address, that data is actually passed to be written back to the register via the same multiplexer, but this time the mem2 reg will have a different value, because this time the data that is going to be stored in the register RT, that is coming from the memory. So this is a load word instruction. It completes on the write operation on the register file as well. Similarly, there is another instruction called store. Store word is just like load word, but it's a little different because of the fact that the data is not written in the register to complete it. It is in fact written in the memory. So what happened in store word? Store word has the same format. First register is the RT. The second is actually the base address and the offset that calculates the address. So first portion is the same. RS plus offset calculates the address. That address is passed to the memory. Second thing is important here. This T is now the source, not the destination. So what happens? Where is this RT? That S2 register is actually read from the register file in the first step in from register. So this RT is basically transferred to the write data field of the data memory, and the memwrite command is passed so that the memory is written with which data. That data is actually coming from the RT register. So this is how a typical R-type load word and store word data path works in the next step. And all these instructions, they complete on a write operation. So whatever it finishes at some write operation, that completes the instruction. So this is a full data path that actually we finished the last lecture on this slide. So this is a complete data path. We can see there are some blue signals here. These are the control signals that actually control the flow of data, whatever the different tasks that are going to be performed according to different instructions. So we will see how these data control signals, how they are generated, how they come, and how are they going to influence the flow of data in the data path. So first thing, let's just review our understanding of the ALU control. The same 4 bits for ALU control that we studied in the ALU, but the one thing we should see that we should know that ALU control 4 bits, they do these tasks, these basic functions, and or add, subtract, and set on less than, and NOR operation. So NOR operation was a little different with the basic understanding, because in NOR, a simple NOR operation is AND operation with inverted inputs. So just invert the inputs, like invert all inputs, and it becomes a NOR. So these are the 4 control signals for ALU, and we know these instructions, how they are going to be performed by these ALU control. Uh, for R type instructions, these ALU control will decide which instruction it is, but for a load one instruction, we know what ALU is going to be doing. So an ALU will do a simple addition stuff for both load word and store word instruction, that we know. So the ALU control is fixed for load word and store word instruction. Similarly, for a branch instruction, we know what it's going to do. It's just simply doing the subtract operation to get the result for branch equal. So it's a simple subtract operation. So these 2 things are fixed. For other instructions, the ALU control will decide which function is going to be performed. So what happens, there is a main control, and there is a ALU control. So we know what ALU control does, but there has to be some information from the instruction, which instruction it is. So that instruction information comes from the field of opcode from the 32-bit instruction of MIPS. So we know what an opcode does. So we have got different opcode values, the 6-bit value in the instruction for different instruction. For load word, it's fixed, it has a specific value. For store word, it has a specific value. For branch equal instruction, it has a specific value. For all the R type instructions, for different instructions, for different R type instruction, it has different value. It has the same single value, which is all zeros. So all the R type will have the opcode of 0, but how do we know which instruction it is? It needs a special field in the instruction called function, that we actually studied in the instruction set. The function field actually decides which operation it's going to be performing. So for an add instruction, the function field is different. For a subtract instruction is different, and or and set less than. All the R type instruction will have different value in the function field. So let's just see this ALU op. It actually comes from the main control unit. So main control unit only depends on opcode. So it's basically a box, a black box, that has an input. ALU main control unit has an input which is opcode. So this comes from your main instruction, and it actually generates a set of instructions according to the type of instruction it is facing. So whichever opcode is it will generate a set of instruction, and of those instruction, one of those control signals, there is one signal called ALU op that actually goes to ALU control unit. So what happens in ALU control unit? ALU control unit actually checks what value of ALU op is it. If it's 00, that means it's a load word. If it's a store word, it's again 00. That actually shows that it's going to do an addition. So ALU op will do an addition operation if the ALU op will have 00 value. That means it's either load word or store word instruction. Similarly, if its value is 01, it means it will do it's a branch instruction, and it will do the subtract operation. If it has gotten a value of 1 0, it means now this different. It's different. It has to see function field as well. So whatever the function field is, this will decide what operation it's going to perform. So according to different function fields, according to different R type instruction, it will generate different ALU function, ALU control signal, ALU, the 4-bit control signals of ALU. So for add we know, for subtract we know, for different operations we know which value is going to be. So this is your main control unit. So what are the inputs to the main control unit? It's like I said, it's just a simple uh, black box with the input with an opcode field. So this is actually the opcode field, the last 6 bits, bit number 26 to 31. So these 6 bits are actually the opcode field that decide which instruction is it. So similarly, we have got a value of 0 for all R type instruction, for value of 35 for load, and 43 in decimal. These are decimal numbers for store instruction. Similarly, we have got the value of 4 for branch instruction. We have got a value of 2 for jump instruction, and so on. There are so many instructions that can be that are actually implemented using this opcode. So for an R type of instruction, we have got an opcode of 0. It means the function field, these 6 bits of function field will decide which operation it's going to perform. Rest of the field we know what these fields does. We have got a RS, source register first, RT, the second source register or destination register for load store instruction. Then we have got an RD for R type instruction. The destination is RD, shift amount, and function field. For load and store instruction, there are 2 registers. One is RS, the other is RT. RT is considered as destination in this number. So these are just 5 bits because we know that we have got 32 registers. We need 5 bits to represent each register. So for branch, the information from the opcode, that is important part. So opcode gets has got the information about the instruction. Either it will be 0 or it will have some value which decides which instruction it is. So for our subset of MIPS instruction that we are implementing in we are studying actually. So these are load, store, branch, and R type instruction, as well as jump instruction. So for these are the different values of opcode. R type of 0 means it's an R type instruction. Opcode of 0 means it's an R type instruction, which means the function field will decide what it's going to do. So there is the constant field or address for our load store instruction. That constant is the 16-bit constant, that is the value, the constant value that is used as offset for load and store instruction. It's a sign value. It's a signed 16-bit number, so it means it's when it's extended to 32-bit, it's actually extended with sign. So if it's a negative number, it will be extended with ones, and if it's a positive number, it will be extended with values of 0, whatever the value in the sign bit is. Same is true for branch. Branch will also have the constant value as the 16-bit which is used. So write for R type and load for R type instruction, the destination is RD, and for load word instruction, the destination is RT. So RS and RT is usually, RS is always the read register, RT is mostly read, but except in the load instruction where this RT is the destination. So let's just see how it goes. So this is actually the basic data path without jump instruction actually. So all these instructions are actually implemented in this whole data path. So the branch instruction is also there, the load word, store word instructions are there, the R type instructions are there, and these are the different control signals which are generated by the control unit. So we have got this control unit here that has only one input, That input is, you can guess, this is your opcode. So this is your opcode. I just write is OP for opcode. So that opcode is the input of the control unit, and it will generate all these control signals accordingly for every instruction. So this is a single simple implementation. It means all these different modules, they will do according to the instruction which is given by the opcode. So for an R type instruction, these will have different values. So we can see which instruction for let's say, let's just start with an R type instruction. What happens in an R type instruction? R type instruction means after the instruction fetch, the instruction, there are few things that are done here. The first thing is RS is passed here. The value, the register number of RS is passed to register 1. RT is passed here. So that means that this is the by default thing. So RS and RT are there. So let's just see what happens next. So after that, the R type instruction, the first input of ALU is RS. We know that this is RS. So this is always going to be RS. The second input is important. Second input will be RT, that is coming from the register file. So this is RT. So it means we have got the first multiplexer here, which is got a resource. So what will be the value of this control signal in this scenario? For R type instruction, a source will have a value of 0. So this is the value for a source multiplexer select signal. So what happens next? So this means this is selecting the first input, or RT, from the register file. So ALU, now the second part, ALU control. We know what happens to ALU control. ALU control will have 2 bits coming from ALU, the main control unit. These 2 bits actually decides, they say that this is our type instruction. The rest of the bits for ALU control. So we have got a separate smaller control unit for ALU that decides, like we just saw here. This is actually what it's going to generate the final control signal for uh, your main ALU. So what information it needs? It needs further information for function field if it's an R type. If it's a load word, it will generate an add control signal. If it's a store word, it will generate add. If it's a branch, it will generate subtract. But if it's an R type, it will need function field. So for function field, we need this second input. This is your function field for ALU control. So this will generate what operation it's going to perform, because it's an R type instruction. So ALU does some work, ALU gets generate a result. Now what happens to this result? This goes to this multiplexer. So there is another multiplexer which is called mem2reg. So mem2reg will have a value of 1 or 0. It will also have a value of 0. So that this value is actually going back to be written back to the register. So this is written back to the register file. But which destination register is going to write on? It will be decided by this small multiplexer. So that this multiplexer comes it needs a control signal called register destination. So register destination will either have value of 0 or 1. For 0, it means the destination is RT, and we all know where RT is the destination. It's a instruction where this is the instruction, load instruction, where the destination is RT. Otherwise the destination is RD. So this means this will select the destination as RD here. So this register destination will also have value of 1 for an R type instruction. So this will be going to be the value of this register destination for R type instruction. So this is how R type instruction works. Similarly, we have got load word instruction. All the things are similar, but a few control signals will be different. First of all, the read register 1 will select RS. There will not be any read register 2 read. It will be read, but it will not be used. So that's why it's grayed out here. So first input to the ALU will be RS. The second input will come from the constant. That is your offset. So that constant comes from the instruction 16 0 to 15 is constant bits. They are extended to 32 and they are passed to ALU through this multiplexer. So ALU source will have a value, different value this time. It will have a value of 1. So what does your ALU does? ALU is calculating the address. So after calculating address, it passed to the memory. And for memory, either it will be a read operation or write operation. So mem read or mem write. For load word, it will be mem read. So mem read means this read data will have the value that is stored in the address specified here. So that value is now written back to register, and this mem2 register will have a different value as well. And same is true for the destination. Register destination will also have a different value. So that's actually how our load word instruction completes. So we can also see a store word in a similar fashion. We can see what different instruction, what different control signals are doing for each step. Similarly, we have got a branch equal instruction. Now this is a little different instruction because this instruction completes at the write operation of program counter. So what happens here? Branch equal instruction, we know that we have got an RS and RT, so we both need RS and RT here. RS and RT are fetched to the ALU by selecting this ALU source as well. The ALU is doing operation of subtraction, that is understood, that is coming from this ALU op. ALU is doing subtraction, and after subtraction it's generating a result of 0. That 0 means that this AND gate is now effective. It will see branch instruction. For branch instruction, this branch control signal is set to 1, and if both the condition and the branch signal is there, it will actually route this value back to, this is actually the branch target address calculated by this ALU, and this data will be transferred back to program counter for branch equal instruction if the conditions are true. If the condition is not true, this PC plus 4 will be the data that will be written to the PC. So program counter is either written PC plus 4, this is your default, or if it's a branch instruction and the condition is true, this will be PC plus 4 plus the branch target address. So this is how a branch equal instruction works. Similarly, we've got jump instructions. Jump instructions are a little different than branch instructions because we have got the whole address, or in fact 26 bits of the address where it's going to be jumped. So program counter will be updated with the new value, the new address, but it's not the branch target address that's like in branch equal instruction. The branch target address is calculated, but for jump we have got 26 bits right here. The remaining 6 bits we can have 2 zeros on the right, because we know that we have always have 2 zeros on the right, so these 2 zeros are there, and the remaining 4 bits, they come from the top 4 bits of the old PC. So current PC 4 bits are also used. The 4 bits of current PC, the most significant 4 bits of the current program counter value are used. Then 26 bits come from this address field, and the last 2 bits, which are always 0, so they are used. So they just concatenate these 3. They just connect together and make the 32-bit address that is actually done here. So this is actually the data path with the jumps added. So jump instruction is also included in this data path. So you can see this is your, so when there is the jump instruction, this multiplexer bypass everything, there is no other module used. It will just see this is the jump instruction, this is the control signal that will be set to 1, and it means that whatever that branch target the jump address that will be stored back to program counter, that will be your program counter update, and the jump instruction completes. So this is the complete data path with all the instructions, with all these instructions, load word, store word, R type, branch equal instruction, and jump instruction. They are all added to this data path. So this is actually the first part, the single simple implementation that is complete right now. So what's next? There has to be some performance issues. Basically, in this, we have some idea of the clock cycle at which this whole system will perform. Remember, in the last lecture, we saw the clock methodology. What does simple sequential circuit design with registers? There's some clock cycle involved in every such system. These clock signals are used for every processor. So what is the clock period that actually is needed for this whole computer to work? So that clock has to be at certain frequency. It cannot be too fast, it cannot be too slow. If it's slow, then it means it will not work with good performance. But if it's too fast, it means it will be causing errors. So what is the ideal speed that a clock cycle should be? A clock signal should be. Uh, this is this is what we studied in the last lecture. Uh, let's just So this is your last lecture. We saw clocking methodology. So state element, actually there is a combinational block. We have combinational blocks as well as state elements, which are the registers and memories. So the clock speed depends on the slowest combination block. So slowest combination block comes from in this scenario, the slowest combination block comes from the longest path of the instruction. Which instruction takes the longest path, that will decide the clock period. So which instruction takes the longest path, we can see which instruction takes the longest path. Longest path means all the modules used in those. So for an R type, the path is simple: instruction memory, register file, ALU, and back to register file. So these are the 4 modules used. For a load word instruction, instruction memory, register file, ALU, and data memory, and then back. So these are the 4 modules. Similarly, for branch, instruction memory, register file, ALU, and back to PC. So it means you can see in these instructions, this is load word instruction that takes the longest path, that decides which instruction is what the clock cycle should be. So that clock cycle will have the combined time that has to be slower than the combined time of instruction memory, register file, ALU, data memory, and all these multiplex LUs. So that time, that clock period should be slower than the combined time of all these modules. So this is actually the performance issue that we have to deal with. The critical path is the load instruction. It means instruction memory, register file, ALU, data memory, and register file. The clock period depends on the time for all these. Not feasible to vary period for different instructions, so we cannot have a smaller clock cycle for load word for R type instruction or branch instruction, and a bigger clock period for load word instruction. So we can only have the one clock period for all the instructions, and that is decided by the slowest instruction. So that is one reason that is not a very ideal design. So we will study more implementation than compare the performance, and those implementations are important because we actually will compare the performance with single cycle for further development in the design. So one thing, this first part is now complete. Uh, you have to do some exercise problems. And assignment is being uploaded on the assignment portal on Microsoft Teams. So I'm just putting another task for you to do. That is based on the last two lectures that we have done about the processor. So these are actually include few types of problem that you are going to be asked. Um, those problems those exercise problems, actually there are a few simple types of problems. One of the type of problems is actually to find the values of the control signal for different instructions. For example, these are different instructions. You have you are asked to get the values of different control signals for each of instructions. These are the simplest type of problems. Similarly, there are few problems like this. When we have got the few instructions in the data path, we want to include a new instruction that is different from the subset of instructions that we have done, a new instructions, and we need to add this instruction to the existing data path. What changes we need to do? This is what challenging question. It can be challenging at times, but you can add as many instructions to the original data path just by changing some small details. Similarly, we have got time delays and latencies of different modules. We can actually get the time for the clock period time for this design by calculating all the latencies of different modules. And finally, we compute the performance using the execution time for instructions. So execution time is important. For a number of instructions, we can get the total time from uh, uh, your latency and stuff. So that's it from this first part. You just try to do the exercise, the assignment questions, the assignment problems, do some more practice on the exercise questions, and you'll learn a lot about processor. So this is what we're going to discuss in the sessions, the live sessions as well. So I hope that you actually take the lecture before coming to the live session. Okay, see you guys then. Love it.